Teruo Kawai of Japan has produced an excellent design of electric motor. It is patent US 5,436,518, issued in July 1995. It's special in that it generates much higher output power than the input power needed to power it. It's an interesting design which has got 4 sets of 3 stator magnets surrounding a rotor which has got 3 magnetic poles. The method of generating 3 outward facing north poles in the stator is a little unusual, but it obviously works very well. Here is an outlet or an outline diagram of the complete motor. The left hand part of the diagram shows the front face of the motor with its 12 red electromagnets of the stator surrounding an unusually shaped steel rotor which is shown colored in yellow. The right hand part of the diagram is a cross section through the motor as shown by the line here for the cross section marked 2. So this is the cross section here. You have a horizontal axle, and the 2 yellow rotor pieces are keyed presumably into the horizontal shaft itself. Shown in blue here are 4 electromagnets, four permanent magnets which have got their north face facing the mild steel rotor piece here. So the north is on this side, the south is on this side. North, south, north, south, north, south. The blue rectangles are, as I said, permanent magnets, but he describes them as being a ring of magnets, although it's not immediately obvious why a ring magnet should not be used. Perhaps none were available with the necessary diameters. He also says that the magnets are bolted to the rotors, which will be keyed securely to the horizontal axle. The frame material supporting the ball bearings and electromagnets is any suitable non-magnetic material, and while aluminium is mentioned, I would strongly recommend that neither aluminium nor copper is used, especially since plastic chopping board material is very cheap and very robust. It is thought that aluminium is non-magnetic, but in actual fact aluminium is strongly magnetic, even though magnets do not stick to it. It has a very negative effect on magnetic fields. In fact, Howard Johnson produced a very nice and very effective permanent magnet only motor, which worked very well indeed. But when he went to create a pre-prototype version of the motor ready for manufacturing, he found it wouldn't work. The reason being that his original was built with wood, which is non-magnetic, and he used aluminium for the pre-production prototype, and the aluminium has a very destructive effect on the magnetic fields in its immediate area. But anyway, coming back to this particular motor here, the steel rotor is made of 2 of these shaped pieces shown here in yellow, and you see the orientation of the permanent magnets bolted to it. North is facing the steel rotor and south is facing away from it. The actual arrangement is that the coils themselves are wound between the 2 end supporting pieces of this particular arrangement. Because each of the inner magnets are attached to steel rotors which are 3 poles each. You get 3 north poles at one end and 3 south poles at the other end. The axle of the motor is good quality stainless steel, and as that is both robust and non-magnetic, it works very well. The switching of the supply current is similar to that of the method used by Charles Flynn with his magnet motor, and Teruo's motor has been measured with a coefficient of performance over 3, which means that the output power is more than 3 times that of the input power. The input power switching occurs 4 times per second, or 4 times per revolution I should say, and it occurs just as the leading edge of the rotor arm approaches an electromagnet. In this particular arrangement here, in this diagram, the part shaded in grey is his representation of the most powerful part of the magnetic field. The electromagnets marked in blue are powered up, and so they are strongly attracting the north pole of the rotor, which is shown here in yellow, and that tends to draw it across. But as soon as the leading edge of this yellow rotor reaches the trailing edge of this stator electromagnet, the current is switched off to that particular group of 3 electromagnets, and then the electromagnets marked 1 are then powered up, and the process continues, and that causes the rotation of the motor. In this particular diagram here, the electromagnets shown in blue have just been powered up, and that draws the yellow rotor arms in a clockwise direction towards the powered up electromagnets. The magnetic force is in attraction mode, and while this is slightly less powerful than repulsion mode, it does not have an adverse effect on the magnets, whereas repulsion mode can, after some years, diminish the power of the permanent magnets. The switching suggested at the same time for each of the electromagnets is, according to his patent arrangement, is using a timing disc as shown here, and the timing disc is very effective. There's a sensor in this bottom mounted section here, and that detects the rotor passing through it. There's a slot in the rotor which allows the switching to occur. While he shows various alternate versions of the motor, he states that the result of a test run on his motor using pure steel as a magnetic material, steel was 30 millimeters thick with teeth of 218 millimeter diameter and notches of 158 millimeter diameter. A 1000 Gauss ferrite magnet was used as the permanent magnet. Electric power of 19.55 watts was applied to the electromagnets, that is 17 volts at 1.15 amps. This produced 100 revs per minute with a torque of 60.52 kilogram centimeters, and that is an output of 62.16 watts. While Teruo suggests doing it that particular way, I would suggest perhaps that you might use a rotational speed which is determined by the power supply and an adjustable electronic circuit. A simple power supply would allow you to give speed control. The speed control is adjusted by the variable resistor here, which is 2 megohms. The pulsing system, which is used in this particular input, goes in at pin 14. You arrange this chip, which is a CD4022BC chip, to give 4 particular outputs, one after the other. This is a divide by 8 device, but if you connect pin 11 to pin 15, it acts as a divide by 4 chip, and it has 4 sequential outputs here. The people who make chips like to think of the first output as 0. Personally, I would think of it as 1, but anyway, the outputs then are 0, 1, 2, 3, 0, 1, 2, 3 in sequence. The 0 output is taken from pin 2 of the chip. The 1 output is taken from pin 1 of the chip. The 2 output is taken from pin 3 of the chip, and the 3 output is taken from pin 7 of the chip. That is an effective way of getting the sequence that you want. The output 0 is connected to the blue electromagnets in the previous picture here. Those blue electromagnets are the ones which are connected to the 0 output line. They're wired in parallel so that they get the full voltage across each of them. The 1 outputs are connected to the electromagnets marked 1, again in this diagram above. The 1s are the electromagnets which immediately follow the ones marked in blue in his particular diagram. The 3 output is connected to the electromagnets marked 3, and those are also connected in parallel. The CD 4022BC divide by 8 is made to act as a divide by 4 by connecting its pin 15 to its pin 11, and so the 4 sets of coils are powered up one after the other in a continuous sequence. Teruo was in a meeting in America discussing getting his motor design manufactured, when the meeting was gate-crashed by members of Japanese organized crime, who intimidated him to such a degree that as a result his motor was never manufactured. One could see a large version of this motor being used to produce a fuel-less cycle, possibly motorcycle, possibly electrical bicycle. The notes that I'm trying to read from here are available to you if you want to download them. They're at www.freeenergyinfo.com/KAWAI.pdf.